Scientific studies indicate that our solar system is about 4.6 billion years old. How did they make that estimate? Scientists use processes called radiometric dating to help them determine the age of rocks that are found on Earth, the Moon, and meteorite samples. By comparing the ages of these materials, scientists are able to draw conclusions about the age of the entire solar system. Radiometric dating uses radioactive elements to help determine the age of rocks and sometimes fossils by measuring the age of radioactive elements found in them. It works like this. Radioactive atoms are naturally unstable and release subatomic particles like neutrons, protons, and electrons. As they do this, they become or decay into other elements. Radioactive carbon, for instance, decays into nitro. In any given example of material, we can expect a certain percentage of each element's atoms to be radioactive. By checking to see how much radioactive carbon is in a sample and comparing it to what should be in there, we can see how much has already decayed into nitrogen. Once we know the missing quantity of carbon, we can calculate the amount of time it has been taken for the radioactive carbon to turn into nitrogen. That tells us how old the material is. Living things are made up of large amounts of carbon, so scientists often use radiometric dating of carbon to calculate when an organism died. This method works for organisms that lived up to 70,000 years ago. However, radiometric dating does not work on living organisms because they are constantly exchanging carbon with the atmosphere. After death, there is no new carbon being brought into the organism, so the decay of products begin to build up. Let's take a closer look at how radiometric dating works, using carbon dating as an example. There are several types of radioactive carbon, with some decaying in just minutes or hours. The carbon dating referred to here is called carbon-14, which is often used to date rocks and some fossils. The process of carbon decay does not happen quickly. In fact, it takes 5,730 years just for half the radioactive carbon in a sample to decay into nitrogen. This time is called the half-life of radioactive carbon. The concept is pretty simple for the first half-life, but it gets more complicated after that. Imagine you have a 100-gram sample of radioactive carbon. If you could check on that carbon after 5,730 years, you would have 50 grams of radioactive carbon and then 50 grams of nitrogen. If you could come back after another 5,730 years, a total of 11,460 years, you would find that half the carbon from the previous time had decayed, so you'd have 25 grams of radioactive carbon left. Then, another 5,730 years later, you would have 12.5 grams of radioactive carbon. As time goes on, the amount of carbon you get would get smaller, but it would take a very long time for the carbon to completely decay. Radiometric dating is extremely useful when combined with the kind of fossil dating, relative dating. While it is helpful to know that one fossil is older than another, that by itself is not a reliable indicator of how long ago the creature lived. If one Earth's layers fossils are 2.2 million years old, though, and a higher layers fossil are 1.3 million years old, it is a reasonable assumption that all fossils found between the layers are between 1.3 and 2.2 million years old. That helps scientists group fossils around the world into their respective eras and periods and helps give a more complete picture of Earth's history. Scientists who study rocks need to be selective when choosing a radioactive element to make sure the half-life is long enough. Radioactive potassium, or potassium-40, turns into argon as it decays, and its half-life is 1.28 billion years. By comparing the amount of radioactive potassium to the amount of argon in the rock sample, scientists can determine the age of the rock. Several other elements or combinations of elements can also be used to date very old objects. In Western Australia, the ratio of lead to uranium was used to date crystals called zircons. In zircons, the ratio increased with age. Some crystals were dated at more than 4.3 billion years old, making them the oldest substance found so far on Earth. Within the zircons, tiny ancient diamonds were found. While the diamonds were too small to have any commercial value, they were invaluable for understanding what Earth may have looked like more than 4 billion years ago. Some scientists point to their structure as evidence that cooler temperatures, liquid oceans, and rocky continents set the stage for life early in Earth's history. In their efforts to determine the age of the solar system, scientists have not limited themselves to studying Earth. They have also studied rocks from the moon. Many of these samples were collected during NASA's Apollo missions. Scientists have determined that the oldest of these lunar rocks are between 4.4 and 4.5 billion years old, which indicates that the moon is about as old as Earth. By studying rocks deep inside Earth, scientists can better estimate the age of the solar system, though this has proved to be a difficult task. Ancient rocks in Earth's crust undergo intense heat and pressure, causing them to change into metamorphic rocks. This sometimes resets the radiometric clocks, such as the metamorphic rocks date only as old as the time of their metamorphism. The age of the parent rock cannot be detected. However, ancient meteorites that have fallen to Earth have never undergone metamorphosis. We can trust them to be good indicators to the age of the solar system. Using radiometric dating, scientists have determined the age of more than 70 meteorites, all of which are about 4.5 billion years old. As scientists study new material samples from other places in the solar system, testing those samples may help determine a more precise age of the solar system and explain how it has developed since its origin.